Is it true? If you only knew the magnificence of 3, 6, and 9, you will have the key to the universe? Oh, let's see. If you only apply the digital root rule and the number system, for example, a multiplication table, simply 9 by 9, and you apply the digital root rule by summing the numbers, you will approach the 3, 6, and 9 as it looks like a hashtag. But I want to show you, this is only 9 by 9. I want to show you how it looks like when you go 27 by 27 or more. And you'll see more unique patterns that's never been pointed out before. I'll show you. Okay, so this is a multiplication table 27 by 27 is under a digital root rule, which is just literally summing the multiplication table. And you get unique patterns, which is I mentioned earlier, which is 13 of them, which is hello 13. Okay, so 3, 6, and 9, it has a 13 different patterns in the number system, which is in the multiplication table. And I point out for you, if you go this way, consider this is north. No, which is it is, we face in north. And this is west, and this is east. So if you go just from north, south, west to east, then you get a 9, a digital root of 9. North, south, east, and west, you can only get 9, which is, I'll explain it in a minute, and I show you exactly that unique. Now, okay, now I have a different approach about the 3, 6, and 9. That's most videos on the net showing the same scheme, this diagram about 1, 2, 4, 8, 7, 5. But I do have a different approach. And yet, this is nothing but a Pascal triangle, which is in front of you showing here. If you look at it, equal the same thing. 1, 2, 4, 8, 16, 32, are the same sequence. But what I discovered, the 3, 6, and 9, that appears on the multiplication table, but you have to apply a digital root rule on the multiplication chart, which is I'll show you in a second. Okay, here is the multiplication chart, the actual one, before I apply a digital root rule on the system number, which is almost every notebook. You can see that multiplication chart. I'm very familiar with the whole word, I guess. So all you got to do when you apply a digital root rule, which is you sum it, you reduce the number. For example, when you come like, okay, 2, 4, 6, 8, 10, okay, it's double digit now. So 1 and 0 is 1, 12 is 3, 14 is 5, 16 is 7, 1 and 8 is 9, 20 is 2, etc. And anyone, you feel like this one, 54 is 9, 4 and 9, 49 is 13, which is 4. So that's what I'm trying to say. It's going to look like this if you apply it on all the numbers, which is this one is only 18 by 18 digital root of multiplication chart. And you will see the 3, 6, and 9 as a infrastructure, a periodic infrastructure. And even if you go 100 by 100, it's going to look the same thing. And yet, this is not what I'm trying to point out. The 3, 6, and 9, it appears in the core of the system, which is if you go up and down, left, right, you're going to run up to 9. You start from any point. like from 369, 369, 369, you add it together, you're going to end up being 9. Or 5, 7, 3, 1, 8, 6, 4, 2, 9, 7. That repeats itself again. 7, 5, 3. But if you add just between 9 to 7, it's going to come up to 9. Same thing, left and right. Patterns that I found out. And if you go like from northwest to southeast, if you count it this way, then you get a digital root of 6. Okay, now we explain the digital root of 6, where it appeared. Mentioned earlier, the top and the bottom is 9, left and right is 9. So now we're going to see where the 6 it appeared. For example, like a digital root of pretty much a square any number, like square 1, square 2, square 3. The digital root is this one here in the middle, 149779419. Then repeat itself again, 14977. Don't forget, this is a digital root of a multiplication table. And my favorite is this one, the third one, the 386, 683, 989. And 3 8, and repeat itself infinitely. And it'll add up to 60, which is the most interested pattern I run up to. 60. 60 is very popular and known numbers, and is almost a mystery so far. So you go from this side down this way, all the numbers, any number you started, you go 9 numbers and repeat itself again, is going to add up to 6. All of it is going to be 6. Regardless, you go left, go that way, only this motion. So this one we got 9, and this way it comes to 60. Even this one comes to 51, which is 5 and 1 is 6. That's a single digit root. And whatever is going to come up is going to come up to 6, a digital root. Whatever you do, from this side all the way down. Okay, and if you go from southwest to northeast, and you get a 3. Every 9 digits, you add them together, they're going to come up to 3. Okay. And the third option and last, we did already 9 and the 6, so now is a 3, which is 3, it appears the other way. It goes like, so this is 9, and this is 6, but 3 is going to be, you're going to find it here. You start from any point, same thing again. You go like 2, 2, 9, 5, 8, 9, 8, 5, 9, and 2, 2 again. But if you add these 9 numbers, 9 units of numbers, the digital root is going to come up to 3. Any point, and you start from any point. It doesn't have to be the beginning. You can start from here, which is the same thing, the other pattern. You start from here. You start from here, anywhere. You just go this way or that way. You just count 9 of them, is going to come up to 3. Same thing, same case on this way. So I don't think this has been found anywhere or mentioned anywhere. So let's see what happens. And I'll show you in a minute. I don't think this has been pointed out anywhere. I've been looking for many, many years. So let me show you the other patterns. Okay, so now we go back to explain where the 3, 6, and 9 appears in the number system, like multiplication table. It appears in a lot of places, but right now I'm just going to show you how it appeared in multiplication table in 13 different forms. Well, one of them is all 9s, but considered 13. So let me show you how. So, okay, so you have a multiplication table right now, right here, under the digital root, all like single digit. So as I explained earlier, if you go up and down with it, like north, south, and west, with east, you will get 9, which is this one here, as you see. You can pause and calculate. So all the ones goes up and down, left, right. It add up to 9. Okay, and the second one, which is the most common one we use as a addition of a multiplication table, you can call it north west to southeast, which is this position right here. It add up to 6, which is starts from here and repeat itself. You can pause and calculate, as I mentioned. So the third one, which is 3, is the other way around. If you calculate all the numbers this way, which is from southwest to northeast, and it's going to come up to 3. You add them together, they're going to come up to 3, as you see right here. Okay, so I want to point out one more thing about 3, 6, and 9 that appears in Fibonacci sequence number when you apply a digital root, which is by summing the number, same thing. As I mentioned earlier, you can pause and calculate, you know, that 1, 1, 2, 3, 5, 8, then goes down. But if you try all the possibilities, you will approach the 3, 6, and 9. Go this way, that way, same thing. That's in Fibonacci sequence number. And I approach one more thing. I approach a letter F, which is Fibonacci, upside down, but that doesn't mean nothing to everyone. That's all I want to point out.
Galileo, way back in the Renaissance, already remarked that nature seems to be a book written in the language of mathematics. This all came after Galileo, so why are we discovering even more and more mathematical regularities out there? What is it telling us?